This is part 4C. Again, we have quadratic equations, terms that have squared as their highest power, and we're looking to solve them. And whenever you're solving a quadratic equation, you're doing something interesting. If you think of the parabola graph, what you're doing is you're saying where does it cross the x-axis. So you're finding the 2 points where it crosses the x-axis. And if you think about parabolas, there are some graphs that cross twice. There are some graphs that might just touch it. We'll pretend that that touched it there at 1 point exactly. And there's other graphs where you might miss the x-axis altogether and there's a gap there. So you might have 2 solutions here. You might have 1 solution, kind of like this tries to be. And you might have no solutions, never touches the x-axis. So with all of these problems, if it cannot be solved, that would be a no solution situation. To solve it by factoring, what we're going to do is our traditional factoring that we're used to, but before we can start any problem, we always have to make sure that we get one side equal to 0. Factoring is based on the idea that you have 2 groups of things in parentheses equal to 0, and if you make any of these 2 groups 0, it doesn't matter what's in the other one because 0 times anything is 0. And then same thing in the reverse direction. If you make this 0, who cares what's over here? So by breaking it into 2 factors, it's kind of a tricky math way of taking advantage of the fact that 0 times anything is 0. So let's get this negative 3 away from this side. Let's move it over here, make it a positive 3. And when we add 3 to both sides, we get our same equation, except instead of plus 12, now we added 3 more, we're at plus 15. Now when we factor, we see that we don't have anything in front of that k squared, which means that we're doing a one-step factor. 2 numbers that multiply to 15, add to 8. So we take our 15, 1 and 15, 2 doesn't work, 3 and 5, and that's all our options. 2 that add up to 8, 3 and 5. And we can go straight to our answer. And to do that, we have k and we have a positive 3, k and a positive 5, so k plus 3, k plus 5, still equal to 0. That equal to 0 is important because what we have to do is actually solve it. Our answer is not 3 and 5. This is not necessarily the solution. So once we've used that up here, we kind of leave that behind, and we want to figure out what value of k we plug in to make this a true statement. So the value of k that we'd plug in here is negative 3, because if this is negative 3, this group is 0. Multiply it by this group, who cares what's in there, because 0 times anything is 0. That will make this statement come true. And if you're not sure about why that works, you can look at trying to plug in that negative 3 into the original problem. If we do that, negative 3 squared plus 8 times negative 3 plus 12. And what do? We get negative 3 squared is 9 plus 8 times a negative 3 is negative 24 plus 12. We add that together and we're going to get negative 3. Holy smokes, look at that. That's what the other side is. So it does work. So it is one of the solutions. Now we want to get our other solution. It's going to be what we plug in here to make this group 0, so negative 5. So our solutions are k is equal to negative 3 or to negative 5. Don't be tempted to say k is not equal to these things. We did not find these values in a denominator. These are the actual solutions to the problem. So this is your answer. Now find another problem that has an interesting challenge to it. Let's try number 4. Some of the tougher factoring problems. Again, first important rule with any factoring is that you have everything on the same side before you start. So we see that we have a squared term here. We probably want to work from that side. We want to get that 56p over here, so we add 56p to both sides. And there's no 56, or there's no p term in this side, and then plus 105. And that's all equal to 0. That 0 is very important. If there's anything you can factor out right away, that's always a nice idea. So in this case, if we could divide all 3 of these terms by 7, that would be helpful, and I believe we actually can. 56 divided by 7 would be 8. 105 divided by 7, I believe, would be 15. So let's do that. Let's take a 7 out front, and when we divide everything out, 7p squared becomes just p squared, 56p becomes 8p, and 105 becomes 15. Still equal to 0. Now, if you remember the problem we just did, that looks very familiar. 8k plus 15, 8p plus 15, we have a 1 out front here. So it's again a one-step factoring on the inside. Bring your 7 along for the ride as you do this, and then let's factor our inside here. We have a p with a positive 3 and a p with a positive 5. Adds to 8, multiplies to 15, we're good to go. Still all equal to 0. Now when finding our solutions, we look at what makes either factor go to 0. And again, it's going to be negative 3 and negative 5. So p is equal to negative 3 or negative 5. You might be a little bit confused about what happened to our 7 here. How come that doesn't get used? Why isn't p equal to 7? Well, if we make p 7, we would get 10 over here and 12 over here, and that doesn't multiply to 0. So the key is to figure out what makes the statement come true, what makes this multiply to 0, and that 7 actually has nothing to do with it. So that 7 is completely irrelevant, which is just the way it is. So our two solutions, what we have here, would be negative 3 and negative 5. Same basic process with all of these. Some of these problems you're going to have to use a 3-step factoring instead of the 1-step, but I always try to take a number out front like that 7. If you can right away, it'll save you a few steps later.